In this video, we are going to investigate the detailed chemistry behind the function of hydrogels, which are polymeric smart materials that absorb water, by going through an experiment. This practical is overall simple and fun, yet the results are dramatic. It requires sufficient knowledge and understanding of high school chemistry, including chemical bonding, reversible reactions, chemical equilibrium, chemical kinetics, organic chemistry, and a bit of acids and bases. Otherwise known as hydrophilic polymers, hydrogels have a wide variety of usages and are commonly available as everyday products ranging from hair gel, disposable nappies, garden beads, to even Orbeez, the popular commercial product targeted for children. They are known for being characteristically hydrophilic, and using the popular Orbeez as an example, they can absorb and swell over 300 times its own mass when placed inside a liquid, and the fully hydrated product can become more than 99.9% water in mass. They have also been applied to other areas such as medicine, bioengineering, pharmaceuticals, and agriculture. So how do hydrogels work? In short, hydrogels swell and absorb water without dissolving through intermolecular interactions, mainly hydrogen bonding, with the solution, and cohesive forces inside the polymeric structure. Hydrogels are made of a complicated cross-linked network of superabsorbent polymer chains and are composed of various compounds, including sodium polyacrylate and polyacrylic acid. Orbeez, which will be used throughout this video, is usually a combination of these two with sodium hydroxide and water. The key to its hydrophilic character is the presence of ionic groups in its structure that have a special affinity to water, some of which include OH-, COOH-, CONH2-, CONH-, and SO3H-. On the other hand, the key to its insolubility in water and ability to retain its shape is its complicated, efficient network of polymers. In order to examine the detailed chemistry behind its magical swelling in water, we will focus on the most widely used hydrophilic polymer, sodium polyacrylate. Sodium polyacrylate is just a sodium salt of polyacrylic acid, another commonly used polymer, which will be explained later, with the following formula. The key groups in its polymer chain are the carbonyl COOH group and sodium Na group. When it is placed inside a liquid, the polymer ionizes in water due to its ionic interactions with the molecules, and the sodium detaches from the carbonyl group, and a carboxyl ion, COO-, and a sodium ion, Na+, are formed. Left with negatively charged carboxylic groups down its main chain, the polymer gains a significant polar charge since it contains sodium. Thus, this polar charge allows it to form hydrogen bonds as polar water molecules get attracted to its negative charges, giving it the ability to absorb large amounts of water. A similar process occurs for polyacrylic acid, otherwise known as PAA, another common hydrophilic polymer usually cross-linked with others like sodium polyacrylate in common commercial products. It is a synthetic polymer of acrylic acid, which is just a vinyl group connected directly to a carboxylic acid with the following chemical formula. In a solution at neutral pH like water, its side chains will acquire a negative charge as they lose their protons, giving them the ability to bond with water and retain them. However, although we have seen how these polymers absorb water, how does it physically expand? As explained previously, the carboxyl groups down the length of the polymer are negatively charged. Thus, they repel each other, and the polymer chain begins to unfold. As it expands, further unreacted COOH and Na groups are exposed to the water molecules, beginning a chain reaction. Moreover, these rigid crosslinks restrict the free movement of the chain, even as it becomes hydrated, which prevents the polymer from dissolving. This essentially creates the soft, gel-like structure of hydrogels that we commonly observe. Finally, these bonds are maximally stretched, and the chain will be unable to expand further, and the hydrogel will stop absorbing water. Thus, the polymer's ionic interactions with the liquid solution is essentially in a state of chemical equilibrium, as the intermolecular cohesive and dispersive forces inside the chain are balanced, which allows it to keep its shape. So now we will go on to the experiment, where we will investigate the rate of reaction. So the rate of reaction can be altered by various factors, such as the chemical composition of the surrounding water. For example, the purer the water, the faster and larger the hydrogels will expand. In order to understand this, we must use knowledge from chemical kinetics and the collision theory. The purer the water, the higher the concentration of deionized pure water molecules, which are the reactants, and thus the higher the frequency of successful collisions, or in other words, a higher rate of reaction. Moreover, when the reactant particles and molecules are closer together, they have a greater chance of reacting.